Smartwatches provide users with access to important information like text messages, health data, weather, and other often complex visualizations. The key benefit of smartwatches is that the users can access the information anytime and anywhere because of their constant availability. While the unique size, form factor, and function of a watch has many positive aspects, there are several drawbacks. One of the primary drawbacks is that interacting with data visualizations on a small display can be challenging. Smartwatch data sets can at times be particularly complex, and due to the small display, there are limited interactions that can take place due to screen occlusion and the fat finger problem. This can cause problems for smartwatch users and forces them to interact with their data collected through their smartwatch on their smartphones or computers. We present BezelGlide, a novel suite of bezel interaction techniques designed to minimize screen occlusion and fat finger effects when interacting with common graphs on smartwatches. In this paper, we conducted 2 user studies to explore the efficacy of the BezelGlide techniques. In the first user experiment, to document and understand the extent of the screen occlusion problem with the BezelGlide techniques, we quantified the amount of screen occlusion experienced when interacting with the smartwatch bezel. We did this by capturing images of users interacting around the bezel and analyzing the screen occlusion. We found that the areas of the bezel with at least 90% visibility occurred at 225 to 15 degrees. For study 2, we created 2 bezel interaction techniques in our BezelGlide suite and compared these with the common shift technique. First, we created full BezelGlide. This technique utilizes the entire bezel and draws a line from the user's touch point on the bezel to the center of the screen. When the line crosses data points, it displays the value of those data points on screen. Second, we created partial BezelGlide. This technique utilizes the portion of the bezel that always ensures 90% visibility of the screen based on the results from our first experiment. Here, a line is drawn from the user's touch point on the interaction area to an endpoint by mapping the points along this area to a projection area. We evaluated our 2 techniques with the shift technique used as a baseline. The shift technique is a common and well-known technique that was created to reduce screen occlusion and the fat finger effect. We compared these 3 techniques in both standing and walking conditions to further analyze their use in a common smartwatch usage scenario. For this study, we analyzed both quantitative and qualitative data. We found that the response time for partial BezelGlide was significantly lower when compared to the other 2 techniques for both mobility conditions. Touchpoint data revealed that touchdown locations were popular in the bottom and bottom right locations, even for full BezelGlide. Further, analyzing average distance traveled, we note that partial BezelGlide required a significant decrease in average travel distance to discern the data point. Qualitative data also showed that all participants preferred to use partial BezelGlide. Participants noted that the technique was better due to the lack of occlusion of the graph displayed on screen. We present BezelGlide, a bezel data interaction technique for smartwatches that reduces the screen occlusion and fat finger effect experienced when interacting on small displays. Thank you.